Close your eyes and listen to a clock. Can you hear it? Perhaps it is the rhythmic ticking of an analog watch on your bedside table, a steady, mechanical heartbeat in the quiet of the room. The second hand sweeps in its endless circle, tracing the same path it has traced a million times before, indifferent to the world outside. Or maybe it is the silent, glowing pulse of digital numbers changing on a screen, flipping from 11:59 to 12 o'clock, from Tuesday to Wednesday, from one moment to the next with perfect, unwavering regularity. It is a rhythm you feel rather than hear, a pulse that marks the cadence of your life, dividing your existence into precise, countable units. In the stillness of the night, when the traffic has faded and the voices have quieted, time feels incredibly simple. It feels like a river that flows at a constant speed, carrying us all together from the past, through this exact moment, and into the future. It feels reliable, feels shared, it feels universal. If you are listening to this in New York, the clock beside your bed reads one time. In Tokyo, a friend is sleeping while their clock reads another. In London, someone is watching the sunrise, their clock showing yet a different number. But despite these different readings, you all assume you are drifting through the same current of time, second by second, ticking away at the exact same pace. The clocks may show different hours, but the seconds themselves, those fundamental units, feel absolute. A second in New York is a second in Tokyo, is a second on the moon, is a second near the edge of the Milky Way galaxy. This is what we believe. This is what makes sense. This is the foundation upon which we build our schedules, our appointments, our entire understanding of cause and effect. It is the invisible scaffolding of civilization. For thousands of years, humans have sought to measure this flow. It began with the sun. The ancient Egyptians erected massive stone obelisks, piercing the sky, their shadows lengthening and shortening across the desert sand to mark the passage of the day. They divided the daylight into 12 parts, a system we still echo today. The Babylonians, gazing at the night sky from their ziggurats, developed a system based on the number 60, giving us 60 seconds in a minute and 60 minutes in an hour. Their mathematics was a hymn to the cyclical nature of the heavens. In China, intricate water clocks, or clepsydras, measured time by the steady drip of water from one vessel to another. The flow of water mimicked the flow of time, constant, fluid, unstoppable. These were not just tools, they were philosophical statements. They said that time was something physical, something that could be captured and quantified, drop by drop, shadow by shadow. As centuries passed, our methods became more sophisticated. Monks in medieval Europe needed to know when to pray, so they invented candle clocks, candles marked with evenly spaced lines that burned down at a steady rate. Time became a flame, consuming itself to mark the hours. And then the mechanical revolution began. Blacksmiths and craftsmen built gears and springs, capturing time in brass and steel. The escapement mechanism was invented, a device that sliced time into discrete ticks. Tick, tock, tick, tock. Suddenly, time was no longer a smooth flow like water or a burning flame. It was digital in a mechanical sense. It was counted. It was chopped up. The town clock tower became the center of communal life, its bell ringing out across the fields, synchronizing the labor of an entire village. Everyone lived by the same bell. Everyone shared the same time. The obsession with precision grew. With the advent of the railroad in the 19th century, local time became a problem. A noon in Boston was minutes different from a noon in New York, based on the position of the sun. Trains needed a standard. They needed absolute time. So we created time zones. We drew invisible lines across the earth and declared that everyone within these lines shared the exact same moment. We synchronized our watches. We built factory whistles to signal the start and end of shifts. We connected the world with telegraph cables, sending time signals instantaneously across oceans. We convinced ourselves that time was a commodity, something to be saved, spent, wasted, or managed. We built our entire modern civilization on the assumption that the ruler of time was straight, rigid, and universal. But in all this measuring, in all this engineering, we never paused to ask if the thing we were measuring was actually the same for everyone. We assumed the map was the territory. This intuition that time is absolute is woven into the fabric of our language, our culture, our very perception of reality. It is the assumption that allows us to meet for coffee at 10 a.m., knowing that when your clock says 10 o'clock and mine says 10 o'clock, we will both arrive at the same moment. It allows us to catch trains, to synchronize meetings across continents, to launch rockets with split-second precision. We believe that a second for you is exactly the same as a second for me. We believe that a second for a hummingbird's racing heart is the same as a second for a tortoise moving through the desert, the same as a second for a star billions of light years away, burning in the depths of space. We believe that now is a universal snapshot of the cosmos, a single moment that exists everywhere at once, a cosmic instant that slices through all of reality at the same time. Consider the arrow of time. We remember the past, but we do not remember the future. We see a glass shatter, but we never see shards fly back together to form a whole glass. We see an egg cook, but never uncook. Time seems to have a direction, a flow from order to disorder, from cause to effect. This irreversibility feels fundamental. It feels like a law of nature. Philosophers like St. Augustine pondered this deeply. "What then is time?" he asked. "If no one asks me, I know what it is. If I wish to explain it to him who asks, I do not know." He recognized the paradox. The past is gone, the future is not yet here, and the present is a dimensionless point between them. Yet we measure it. We live in it. We feel it passing. It is a comforting thought. It makes the universe feel orderly, like a well-organized library where every book has its place and every event has its moment. It makes time feel like a vast container, an invisible stage on which the drama of existence unfolds. Events happen in a straight line, one after another, like pearls on a string. Yesterday came before today. Today comes before tomorrow. The past is behind us, fixed and unchangeable. The future is ahead, unknown but inevitable. And we, collectively, all of us, every person, every planet, every galaxy, are standing on the same rung of this ladder, experiencing the same now together. This is Newton's universe. This is the clockwork cosmos that feels so intuitively correct. It is a world of absolute truths, where space is a fixed stage and time is a steady metronome beating out the rhythm of creation. Isaac Newton wrote, "Absolute, true, and mathematical time of itself, and from its own nature, flows equably without relation to anything external." For centuries, this was the dogma of science. But as you lie there, breathing slowly, feeling the mattress support the weight of your body, letting the tension of the day drain away from your muscles, I want you to invite a different possibility into your mind. A possibility that is stranger, yet somehow quieter. A possibility that does not shout or alarm, but whispers. A possibility that suggests this steady river, this absolute tick-tock, this universal now, is an illusion. Not a harmful illusion, not a lie, but a simplification. A useful approximation that works perfectly well for our daily lives but breaks down when we look more carefully, when we move faster, when we venture into stronger gravity, when we ask deeper questions. The river of time, it turns out, is not a river at all. It is something more flexible, something more personal, something more beautiful. Imagine for a moment that the clock on your wall is not measuring a universal heartbeat, but only its own private journey through spacetime. Imagine that time is not a rigid container, but a flexible fabric, one that can stretch and twist and compress and slow down. Imagine that now is not a line that cuts across the entire universe, but a local bubble, a private experience, unique to you and your motion and your position in the gravity well of the Earth. What if I told you that you are already a time traveler? Not in the science fiction sense of stepping into a gleaming machine and vanishing in a flash of light, but in a quieter, more fundamental way. What if simply by standing up from a chair or lying down to sleep or climbing a flight of stairs or driving to the grocery store, you are altering the rate at which you move through time? This is not speculation. It is not science fiction. It is not a hypothesis waiting to be tested. It is the verified, measured, repeatedly confirmed reality of the universe we live in. The universe is calm, even when it is strange. The laws that govern it are consistent, predictable, and elegant. They simply do not match the intuition we inherited from our evolutionary ancestors who never moved faster than a running animal or climbed higher than a tree. Our brains evolved to perceive time as absolute because, for survival purposes, it was close enough. The difference between your time and my time at human speeds and Earth's gravity is measured in billionths of a second. But it is there. It is real. And tonight, as you drift toward sleep, we are going to peel back the layers of what we think we know to find the true nature of time underneath. Let your breath deepen now. Inhale slowly, filling your lungs with the quiet air of the room. Feel your chest rise. Exhale, releasing the tension in your shoulders, your jaw, your hands. Let your eyelids grow heavy. You are safe here. You are anchored in this moment, lying in your bed, feeling the gentle pull of the Earth's gravity holding you down, feeling the warmth of the blankets around you. But your mind, your imagination, is free to wander. It is free to travel to the edges of reality, to the places where time bends and stretches, to the questions that have fascinated humanity for centuries. Is it possible to leave now? Can we travel to the past, to walk among the dinosaurs, to witness the birth of stars? Can we travel to the future, to see cities that have not yet been built, to meet people who have not yet been born? Not in a dream, not in a fantasy, but in the physical world, following the actual laws of physics. The answer is more beautiful and more surprising and more subtle than you might expect. It is not a simple yes or no. It is a story that unfolds in layers. It is a story of gravity, which is not a force but a curvature. It is a story of light, which always travels at the same speed no matter how fast you chase it. It is a story of the geometry of existence itself, the four-dimensional fabric we call spacetime. It is a story that began with a patent clerk in Switzerland asking questions that seemed absurd at the time. It is a story that has been confirmed by atomic clocks flying on airplanes, by satellites orbiting overhead, by particles raining down from the upper atmosphere. It is a story that reaches all the way to the event horizon of black holes and the hypothetical tunnels called wormholes. So listen to the clock again. Tick, tick, tick. Sounds the same. But by the time we finish this journey, by the time sleep finally claims you and you drift into dreams, you will know that each tick is not a universal beat, but a unique coordinate in a vast, shimmering ocean called spacetime. Each tick is local. Each tick is relative. Each tick is quietly, beautifully real. For most of human history, time was a master we could not question. Isaac Newton, the father of classical physics, codified this view with unwavering authority. He described absolute time as something that flows equably without relation to anything external. It was a divine container, a perfect metronome set by the Creator. In Newton's universe, if you removed all the stars, all the planets, and all the light, time would still tick away in the empty void, steady and true. This was the Clockwork universe. Precise, unchanging, eternal. It is the universe that matches our daily experience. Feels right, feels secure. But in the early 20th century, a young patent clerk named Albert Einstein looked at the universe and noticed a crack in this perfect clockwork. He was not a distinguished professor at a great university. He was a civil servant reviewing diagrams for new electrical devices. But in his mind, he was traveling alongside beams of light. Albert Einstein was not always the icon of genius we know today. As a child, he was slow to speak. His parents worried he might be intellectually disabled. In school, he chafed against the rigid, rote learning of the German education system. He preferred to daydream, to ask questions that his teachers found impertinent. He found solace in his violin, playing the music of Mozart, finding a structure and beauty in the notes that mirrored the hidden harmonies he sought in nature. He failed his first entrance exam to the Polytechnic Institute in Zurich. He struggled to find a job after graduation. He was, by all conventional measures, an outsider. But this outsider status gave him a gift: the ability to look at the world without the blinders of tradition. Working at the patent office in Bern gave him time to think. While reviewing applications for new synchronization devices for clocks, he began to ponder the very nature of time itself. He wasn't looking at clocks initially. He was thinking about light. In 1905, his Annus Mirabilis, or Miracle Year, he published 4 papers that would change physics forever. One of them dealt with the electrodynamics of moving bodies. Einstein realized that the speed of light is a cosmic speed limit, a constant that never changes no matter how fast you are moving. This was a bizarre idea. In our everyday world, speeds always add up. If you throw a ball from a moving car, the ball travels at the speed of the throw plus the speed of the car. But light didn't behave this way. Decades earlier, physicists Albert Michelson and Edward Morley had tried to measure the speed of light through the ether, the invisible substance they believed filled space. They built a sensitive interferometer, splitting a beam of light and sending it in 2 perpendicular directions. They expected that as the Earth moved through space, the ether wind would slow down light in one direction. They found something shocking. Light always moved at the same speed, no matter which direction the Earth was moving. It refused to speed up or slow down. It was stubborn. It was absolute. The ether didn't exist. Einstein recalled a thought experiment he had as a teenager. He imagined chasing a beam of light. If he could run fast enough to catch up to it, what would he see? Would he see a frozen electromagnetic wave, oscillating in place but not moving? That seemed impossible. Light is by definition a moving wave. He realized that even if he ran at 99% of the speed of light, the beam would still race away from him at the full speed of light. The laws of physics must be the same for everyone, whether they are sitting still or moving at high speed. This principle, combined with the constant speed of light, led to a paradox that could only be solved by dismantling Newton's absolute time. Einstein took this stubborn fact and followed it to its logical conclusion. Imagine you are on a train moving at half the speed of light. You turn on a flashlight. To you, the beam moves away at the speed of light. Now imagine someone standing on the platform watching you fly by. In Newton's world, they should see the light move at your speed plus the light speed. They should see superfast light. But experiments showed this wasn't true. The person on the platform sees the light moving at exactly the same speed you do. The speed of light is constant. But how can that be? How can 2 people, moving at vastly different speeds, measure the same beam of light traveling at the same velocity? If the speed is the same, but the distance the light travels is different depending on who is watching, something else must give way. Speed is just distance divided by time. If the speed is fixed, then distance and time must be flexible. That something else is time. This was the revelation that shattered the clockwork. Time is not absolute. Time is relative. It depends on how you move. Einstein called this special relativity. He showed that the faster you move through space, the slower you move through time. If you could travel in a spaceship at 99% of the speed of light, years might pass for the people you left back on Earth, while only days would pass for you. You would return to a future that is far ahead of the one you would have experienced if you had stayed home. You would have effectively traveled into the future. This leads to the famous twin paradox. Imagine 2 identical twins, Alice and Bob. Alice stays on Earth. Bob boards a spaceship that travels at 90% of the speed of light to a distant star and returns. From Alice's perspective, Bob's clock is ticking slowly. His heart is beating slowly. He is aging slowly. When Bob returns, he might have aged only a few years, while Alice is now an old woman. This isn't just a trick of measurement. It is a physical reality. Bob has literally skipped over decades of Earth time. He has traveled to the future. His world line through spacetime was shorter than Alice's, even though he traveled a greater distance in space. He traded space for time. The scientific community did not embrace this immediately. It was too radical, contradicted common sense. But the mathematics, known as Lorentz transformations, held up. And soon, a mathematician named Hermann Minkowski, who had once taught Einstein, provided the geometric framework for this new theory. He famously declared, "Henceforth space by itself and time by itself are doomed to fade away into mere shadows, and only a kind of union of the two will preserve an independent reality." He drew diagrams, spacetime diagrams, that showed how time and space were interwoven. But Einstein didn't stop there. He realized that motion wasn't the only thing that affected time. Special relativity only dealt with constant speeds. What about acceleration? What about gravity? He began to think about gravity. He imagined a man falling from a roof. A person in freefall feels no weight. He called this the happiest thought of my life. He realized that gravity and acceleration are two sides of the same coin. This is the equivalence principle. If you are in a windowless elevator in deep space, and a rocket pushes it upward, you feel a force pushing you down to the floor. This feels exactly like gravity. If you shine a light across the elevator while it is accelerating, the floor moves up to meet the beam, making the light appear to curve downward. If acceleration bends light, and acceleration is equivalent to gravity, then gravity must bend light. And if gravity bends light, it must warp the spacetime through which light travels. In 1915, after 10 years of struggle, he published General Relativity, a theory that describes gravity not as a force, but as the curvature of spacetime itself. Imagine a bowling ball placed on a trampoline. Curves the fabric. A marble rolled nearby follows the curve. Massive objects like the Earth and the Sun curve the fabric of space and time around them. And here is the crucial part. Time runs slower wherever gravity is stronger. This was a breathtaking leap. Newton said gravity was a force acting instantly across distance. Einstein said gravity was geometry. The planets don't orbit the sun because the sun pulls them. They follow the natural curves of space created by the sun's mass. This theory needed proof. In 1919, a total solar eclipse provided the opportunity. Astronomer Arthur Eddington led an expedition to the island of Principe off the coast of Africa. During the darkness of the eclipse, he photographed the stars near the sun. According to Newton, the sun's gravity should have little effect on starlight. According to Einstein, the sun's mass should warp space, bending the starlight and making the stars appear in slightly different positions. When the photographs were analyzed, the stars had shifted exactly as Einstein predicted. The news made headlines around the world. "Lights all askew in the heavens," ran the New York Times. Einstein became an overnight celebrity. He had overthrown Newton. He had proven that space is flexible and time is relative. This means that your feet, being closer to the center of the Earth, are aging slightly slower than your head. It means that time flows differently in the basement than it does in the attic. The difference is infinitesimal, far too small for human senses to detect, but it is real. Einstein peeled the face off the clock and showed us the gears, and the gears are made of geometry. We live in a universe where time is personal. It belongs to the observer. What feels fixed is often only familiar. The rigid tick-tock of Newton's universe melted away, replaced by a landscape of valleys and peaks, where time flows like water, pooling near massive objects and rushing quickly in the empty spaces between stars. This shattered our intuition. It opened the door to questions that had previously belonged to fantasy. If time can slow down, can it stop? If gravity curves time, can it curve it into a loop? Can we go back? The first crack in the absolute nature of time let the light of possibility shine through. And it is a gentle light. It does not break the universe. It makes it more flexible, more accommodating. It tells us that our experience of now is just a local perspective, a view from our own little window. Other windows look out onto different times. The universe is calm, even when it is strange. Before we journey further into these curves, let us pause and recap where we are. We began with the assumption that time is a steady river shared by everyone. Einstein showed us that this is an illusion. Time is elastic. It stretches with speed and sags with gravity. This is not a theory we simply believe. It is the operating system of the cosmos. But you might be wondering, is this just math? Is it just numbers on a chalkboard? Or is it real enough to touch? You might be holding the proof in your hand right now, or perhaps it rests on your nightstand, charging for the day ahead. Its screen dark, its circuits humming quietly. Your smartphone. It seems like such an ordinary object, doesn't it? A rectangle of glass and metal that connects you to the world, that shows you messages and videos and the faces of people you love. But inside that sleek device, nestled among the circuits and processors, is a receiver for the Global Positioning System, GPS. This small chip is doing something extraordinary. It is listening to the sky. It is receiving whispers from machines orbiting hundreds of miles above your head. And every single calculation it performs, every time it places that blue dot on your map, is a validation of Einstein's theories. We use it to find the nearest coffee shop, to navigate through unfamiliar cities, to track our morning runs along familiar paths. Feels like magic, but it is actually a triumph of relativity. It is a time machine that fits in your pocket. It is the most widespread, everyday application of Einstein's theories, a silent testament to the warping of time that guides us through our lives. Millions of people use it every day without ever realizing they are relying on the curvature of spacetime to get home. The story of GPS begins not with scientists in laboratories, but with the Cold War. In the 1950s and 60s, the US military needed a way to navigate precisely anywhere on Earth. Ships needed to know their location in the middle of the ocean. Submarines needed to aim their missiles accurately. The first attempts used radio beacons on the ground, but these had limited range. Then, in 1957, the Soviet Union launched Sputnik, the first artificial satellite. American scientists tracked it by listening to its radio beeps. They noticed something. As Sputnik passed overhead, the frequency of its signal changed due to the Doppler effect. By measuring this change, they could calculate where the satellite was. Then they had a realization. If you know where a satellite is, and you can measure how far you are from it, you can figure out where you are. The logic worked in reverse too. This insight led to Transit, the first satellite navigation system, operational in 1964 for nuclear submarines. But Transit was slow and not very accurate. The dream was a constellation of satellites that could provide instant, three-dimensional positioning anywhere on the planet, in any weather, at any time. The GPS system, as we know, it was officially launched by the US military in the 1970s, fully operational by 1995. It relies on a constellation of about 30 satellites orbiting the Earth in 6 different orbital planes, arranged so that at least 4 are visible from any point on the ground at any time. These are not stationary. They are moving fast, about 14,000 kilometers per hour, or roughly 3.9 kilometers per second. They are flying around the planet twice every day in precise orbits about 20,200 kilometers above the surface. Each satellite weighs about 2,000 pounds and is powered by solar panels that unfold like wings. Each one carries atomic clocks, multiple redundant units in case one fails, ticking with extraordinary precision. And each one broadcasts a radio signal that says, essentially, I am here, and the time is now. To calculate your position on the ground, your phone listens for signals from at least 4 of these satellites. Why 4? 3 would seem to be enough, 3 spheres intersecting at a point, but you also need to correct for the error in your phone's cheap quartz clock, which is nowhere near as accurate as the atomic clocks in space. Each signal contains a timestamp, the exact moment the signal left the satellite, encoded in the radio wave itself. Your phone compares that time to its own internal clock. The difference tells you how long the signal took to travel. By multiplying the time difference by the speed of light, which travels at exactly 299,792,458 meters per second. It calculates how far away the satellite is. This distance defines a sphere. You are somewhere on the surface of that sphere. A second satellite gives you a second sphere. The two spheres intersect in a circle. A third satellite gives you a third sphere, which intersects the circle at 2 points. One of those points is usually out in space or deep underground, so you can eliminate it. The fourth satellite resolves any ambiguity and corrects for the clock error. This process is called trilateration, measuring distances, not angles. It draws imaginary spheres around each satellite, and where those spheres intersect is where you are, standing on a street corner or sitting in your bed. But for this to work, the timing must be incredibly, almost unbelievably precise. Light, the fastest thing in the universe, travels 30 centimeters, about a foot, in 1 nanosecond, 1 billionth of a second. An error of just 1 microsecond, 1 millionth of a second, would translate to an error of 300 meters, the length of 3 football fields. An error of 10 microseconds could put you a full 3 kilometers off course. For modern applications, landing airplanes, guiding drones, directing emergency services, such errors are unacceptable. So the system must keep time to within a few nanoseconds. This is where Einstein comes in, quietly, invisibly, essential. According to special relativity, because the satellites are moving fast relative to the ground, their onboard atomic clocks should tick slower than the clocks on the ground. This is the kinematic time dilation we discussed earlier. Time slows down for moving objects. The satellites are moving at 3.9 kilometers per second, which sounds fast but is still only 0.0013% of the speed of light. Yet even this tiny fraction creates a measurable effect. The calculation, using the Lorentz factor, shows they should lose about 7 microseconds per day due to their speed. 7 millionths of a second might seem trivial, but remember, light travels 300 meters in a microsecond. 7 microseconds means an error of 2.1 kilometers. That is the difference between being on Main Street and being in the next town over. But there is a second factor, and it works in the opposite direction. These satellites are orbiting about 20,200 kilometers above the Earth, far away from the heavy gravity of our planet. The curvature of spacetime is gentler up there. The gravity well is shallower. According to general relativity, because they are in weaker gravity, their clocks should tick faster than the clocks on the ground. Time flows faster where gravity is weaker. The calculation, using the Schwarzschild metric for a spherical mass, shows they should gain about 45 microseconds per day due to the weaker gravitational field. This is the gravitational time dilation, the warping of time itself by the mass of the Earth below. So we have two competing effects, two relativistic forces pulling time in opposite directions. Speed slows the clocks down by 7 microseconds per day. Gravity speeds them up by 45 microseconds per day. Which one wins? When you do the math, 45 minus 7, you get a net result. The clocks on the satellites run faster than the clocks on Earth by about 38 microseconds every single day. 38 microseconds might sound like nothing. It is a blink of a blink. It is less than the time it takes for a nerve impulse to travel from your finger to your brain. But remember, light travels incredibly fast, about 300 meters in a single microsecond. If you multiply 38 microseconds by the speed of light, you get an error of about 11 kilometers per day. Let that accumulate for a week, and you are off by 77 kilometers. Let it accumulate for a month, and the system is completely useless. If the engineers who designed GPS had ignored Einstein and used Newton's absolute time, assuming all clocks ticked at the same rate everywhere, the system would drift by about 10 kilometers every day. Within hours, your navigation app would tell you that you were in the middle of a field when you were actually driving on the highway. The entire system would be useless. The airplanes would land on the wrong runways. The ships would miss the docks and crash into the shore. Emergency services couldn't find you. Modern warfare, which relies on GPS-guided weapons, would be impossible. The global economy, which depends on synchronized shipping and logistics, would grind to a halt. But the engineers did not ignore Einstein. In fact, when GPS was first being designed in the 1970s, some engineers were skeptical. They thought the relativistic effects would be negligible. A few argued for launching the satellites without any corrections and measuring the drift empirically. Wiser heads prevailed. They understood the theory. Before the satellites are launched, the clocks are adjusted to tick slightly slower than they would on Earth. The clock frequency is deliberately offset by a factor of about 38 microseconds per day, which translates to a frequency change of about 1 part in 10 billion. They are tuned to sync with the spacetime on the ground. Their heart rate is artificially lowered so that when they are in orbit, experiencing the twin effects of speed and gravity, they appear to tick in perfect sync with Earth clocks. It is a beautiful ballet of spacetime engineering. The satellites know they are time travelers. They compensate for their journey. Every time you look at your phone to see where you are receiving a message from a machine that is traveling through time at a different rate than you. The satellite is aging faster than you. This clock is running in a different temporal rhythm. Yet the message arrives, the calculations are made, and that blue dot appears on your screen, accurate to within a few meters. The accuracy of that blue dot is the proof. Time dilation is not a distant theory confined to textbooks and thought experiments. It is a practical engineering requirement for the modern world. It is the hidden code, the invisible correction factor, that keeps our civilization running. GPS is not the only system that does this. Other systems around the world face the same challenges. Russia's GLONASS, Europe's Galileo, China's Beidou, India's NavIC, and Japan's QZSS. All of these satellite navigation systems must account for the same relativistic effects. It is a universal law that no technology can escape. You cannot cheat spacetime. You must understand it, respect it, and compensate for it. Consider the atomic clocks themselves, the beating hearts of the GPS constellation. These are the most precise timekeepers humanity has ever built, marvels of quantum physics and engineering. They measure time not by the swing of a pendulum or the oscillation of a quartz crystal, but by the vibration of atoms themselves, usually cesium or rubidium, though newer designs use strontium or other elements. Inside the clock, atoms are cooled to temperatures near absolute zero, where they barely move. Then they are placed in a magnetic field and stimulated by microwaves tuned to a very specific frequency. At exactly the right frequency, the atoms jump between two energy levels, resonating like a tuning fork struck at its natural pitch. This oscillation is the most consistent thing in the universe, more regular than the rotation of the Earth, more stable than the orbit of the planets. A cesium-133 atom oscillates exactly 9,192,631,770 times per second. This number, this specific frequency, defines the second in the International System of Units. It is not arbitrary. It is the heartbeat of the atom itself, dictated by the structure of the nucleus and the electromagnetic force. They are the heartbeat of our technological civilization. They do not tick with gears. They hum with the fundamental frequency of matter. And they notice everything. If you take two synchronized atomic clocks, reset to exactly the same time, and place one on the floor and the other on a table just 1 meter higher, and you wait, the one on the table will run slightly faster. Why? Because it is a meter farther away from the Earth's center. The gravity is infinitesimally weaker, the curvature of spacetime infinitesimally less pronounced. The difference is about 1 part in 10 to the 16th power, 1 followed by 16 zeros, but modern clocks can measure it. Time is local, personal, and quietly real. The air near the ceiling is older than the air near the floor by billionths of a second per day. Your head, which spends most of its life a couple of meters higher than your feet, is aging faster than your feet. Over the course of a human lifetime, your head ages about 90 billionths of a second more than your feet. It is not enough to matter biologically, but it matters for the truth of reality. We are all drifting through a gradient of time, swimming in a gravity well that gently pulls the seconds apart, stretching them near the floor and letting them run freely near the ceiling. In particle accelerators like the Large Hadron Collider in Switzerland, protons are accelerated to 99.9999% of the speed of light, whipping around a 27-kilometer ring buried beneath the French and Swiss countryside. At these speeds, time dilation becomes extreme. The protons live in a slow-motion world. From their perspective, time is normal, but to us watching from the lab, they seem to take forever to decay. Particles that would normally disintegrate in microseconds last for hours. The magnets that guide them must be synchronized with nanosecond precision, and the calculations must account for the fact that time is slowing down for the particles themselves. The engineers must calculate where the particles will be, not where they are now, because by the time the signal reaches the magnets, the particles have moved. Without relativity, these massive machines wouldn't work. Without Einstein, we would be blind. We maintain a global time standard called International Atomic Time, abbreviated TAI from the French Temps Atomiques International. It is the average of over 400 atomic clocks located in more than 50 national laboratories around the world. These clocks are constantly compared, their slight drifts averaged out, creating a single universal reference time that is accurate to within nanoseconds. But TAI is not the time you see on your watch. Because the Earth's rotation is slowing down very slightly, about 1.7 milliseconds per century due to tidal friction from the moon dragging on the oceans, TAI gradually drifts away from the solar day, the time it takes for the sun to return to the same position in the sky. To keep our civil clocks synchronized with the sun, we use a different standard, Coordinated Universal Time, or UTC. Every few years, we add a leap second to UTC, pausing the clock for 1 second at midnight to let the Earth catch up. This is a human adjustment, a way of forcing our relativistic atomic precision to mesh with the messy, organic rotation of our planet. It is a reminder that time is both a physical reality, something that can be measured to extraordinary precision, and a social construct, something we bend to fit our needs. This proof is comforting in its solidity. It tells us that the strangeness of the universe is consistent, follows rules. We can predict it. We can build machines that rely on it. We can launch satellites into the sky, and they will tell us where we are because we understand the fabric of spacetime they are swimming through. And if we can rely on the warping of time for our maps, for guiding our cars and ships and planes, what else can we rely on it for? How far can we push this elasticity? Can we warp it more, bend it further, twist it into shapes that let us reach across the stars, or even reach back through the years? The universe has shown us the door. Now we are asking if we have the key. We have established that time is flexible, that it bends and stretches like fabric, that it pools in gravity wells and rushes freely in the empty spaces between stars. We have seen that we use this flexibility every day, that every time you glance at your phone to see where you are relying on satellites that are aging faster than you, traveling through a different temporal stream. The universe has revealed itself to be stranger and more beautiful than our ancestors imagined. Now, we are going to embark on a deeper journey. We are going to drift down the river of spacetime to see where the currents might take us, to explore its tributaries, its eddies, its waterfalls. We are becoming cartographers of time, mapmakers of the fourth dimension, explorers venturing into territories where clocks tick at different rates and the past might touch the future. Over the next hours of this script, or perhaps the next few minutes of your wakefulness before sleep claims you, before your breath deepens and your thoughts begin to blur, we will chart a course through the possible and the paradoxical. We will move from the solid ground of proven science, where every step is verified by experiment, into the mist of theoretical possibility, where mathematics allows wonders we have not yet seen. We will walk the line between what we know and what we dream, between the real and the almost real. Think of this journey as a river with many branches. We begin in the shallows, where the water is clear and you can see the stones beneath. This is the realm of established fact, of GPS satellites and atomic clocks, of muons raining from the sky and light bending around the sun. Then we wade deeper into currents that are swift but still navigable. This is the realm of black holes and time dilation so extreme that minutes become years. And finally, we will float toward the edge of the waterfall, where the river drops into mist and mystery, where wormholes might tunnel through space, where the very concept of before and after begins to dissolve. At each stage, I will be your guide, pointing out the landmarks, translating the language of physics into images you can hold in your mind as you drift towards sleep. First, we will look at the foundations, what spacetime really is, not as an abstract concept, but as a tangible structure, a fabric you can almost touch. We need to visualize the territory we are mapping. Imagine that the entire history of the universe, from the Big Bang to the end of time, is a vast, four-dimensional crystal, every moment frozen like an insect in amber. This is the block universe, and we will walk through it together, understanding how your life is a thread woven into this tapestry, how past, present, and future exist simultaneously in a timeless sculpture. We will learn the vocabulary of spacetime, world lines, light cones, geodesics, the paths that objects follow through the geometry of existence. It sounds abstract, but I promise to make it visual, to give you metaphors you can see behind your closed eyelids. Then we will visit the experiments that changed our minds, the concrete moments in history where skepticism turned into awe, where the impossible became measured fact. These are the historical markers on our map, the lighthouses that guide us through the strange waters of relativity. We will travel back to October 1971 to join Joseph Haffel and Richard Keating as they board commercial airliners with atomic clocks strapped into passenger seats, flying east and west around the planet, testing whether time really does slow down with speed and speed up with altitude. We will feel their nervousness as they land, wondering if their clocks have drifted, if their experiment has failed. And we will share their quiet triumph when the numbers match Einstein's predictions exactly. We will look up at the sky and watch subatomic particles called muons, cosmic messengers from the depths of space, raining down through the atmosphere. By all rights, they should decay long before they reach the ground. But they don't. They survive because they are traveling so fast that time slows down for them. They are living proof, microscopic time travelers arriving at our doorstep every second of every day. We will visit the Jefferson Laboratory Tower at Harvard University in 1959, where two physicists fired gamma rays from the basement to the roof, measuring the gravitational tug on time itself with such precision that the Earth's gravity over 74 feet could be detected. And we will stand in a laboratory at NIST in 2010, where a single step, just 33 centimeters, the height of a stair, was enough to measure the difference in the flow of time. These experiments are not dry facts. They are monuments to human curiosity, testimonials to our species' determination to understand the invisible rules that govern our existence. From there, from the laboratories and passenger jets of Earth, we will drift toward the extremes, to the edges of physics where the numbers become enormous and the effects become dramatic. We will leave the gentle curvature of our planet's gravity well and float out toward the deepest valleys in spacetime, black holes. We will approach the event horizon, that invisible boundary where the escape velocity exceeds the speed of light, where time, as seen from the outside, freezes. We will ask what it means to freeze a moment forever, to watch a clock stop ticking, to see light redshift into darkness. We will contemplate the singularity at the center, the point where the rules break down, where the fabric of spacetime rips and our equations whisper infinity and then fall silent. We will explore the idea that these monsters might not be dead ends but doorways, that inside a rotating black hole, the geometry might twist so violently that forward in space becomes backward in time. We will look at other exotic geometries. The rotating universe that Kurt Gödel discovered in Einstein's equations, a cosmos that spins like a whirlpool, where if you flew far enough you could return to your own past. The infinite cylinders that Frank Tipler imagined, spinning so fast they drag spacetime into spirals. These are not fantasies. They are solutions to the equations of general relativity, blueprints that nature has not forbidden, merely not built, or at least not nearby. They show us that the universe is richer in possibility than our daily experience suggests. Then, as we stand at these extremes, Staring into the abyss where time curves back on itself, we will confront the paradoxes that have haunted physicists and philosophers for generations. If we could go back in time, could we change the past? What would happen if you met your younger self? What if you prevented your own birth? We will explore the famous grandfather paradox, walking through its logic step by step, feeling the trap close around us. But we will not leave you trapped. We will meet the protections the universe seems to have in place, the gentle guardrails that keep reality from collapsing into contradiction. We will learn about the self-consistency principle proposed by Igor Novikov, which suggests that the laws of physics will always conspire to maintain a consistent timeline, that guns will jam and trains will be delayed to prevent paradoxes. We will explore Stephen Hawking's chronology protection conjecture, the idea that quantum effects build up to destroy any time machine before it can be used, keeping the world safe for historians. These are not arbitrary rules imposed by a cosmic referee. They emerge naturally from the mathematics, from the deep structure of causality and quantum mechanics. They suggest that the universe knows how to protect itself, that it has an immune system against inconsistency. Finally, our journey will take us to the frontier, to the bleeding edge of theoretical physics where established science fades into speculation, where the solid ground becomes fog. We will look at the theoretical machines that the equations allow but we have not yet built, wormholes, those hypothetical tunnels through spacetime that could connect distant galaxies or distant centuries. We will learn about the challenges, the exotic matter with negative energy needed to hold them open, the instabilities that threaten to collapse them, the causality violations that might tear them apart. We will explore the Alcubierre drive, the warp bubble that could theoretically carry a spaceship faster than light by compressing space in front and expanding it behind, surfing the fabric of reality itself. We will examine the energy requirements, initially calculated to be more than the mass of the universe, later refined down to merely the mass of Jupiter, and ask whether any civilization could ever harness such power. We will stand at the edge of what we know and peer into the mist of what we don't. We will wonder about quantum gravity, the missing theory that would unify the very large with the very small, that would explain what happens at the center of a black hole or at the instant of the Big Bang. We will speculate, gently, carefully, always distinguishing between what is known and what is imagined, about the ultimate nature of time. Is it fundamental or is it emergent, like temperature arising from the motion of atoms? Could time be an illusion, a side effect of entropy increasing? We will ask these questions not to find definitive answers tonight, but to marvel at the depth of the mystery, to appreciate how much we have learned and how much remains unknown. And through it all, through every stage of this journey from the proven to the possible to the purely speculative, we will return again and again to the clock, to that quiet rhythm of ticking, to the present moment where you lie safely in your bed. The journey outward into the cosmos is also a journey inward, into understanding your place in the fabric. While the universe is vast and strange, filled with wonders that stretch comprehension, you are safe. The strangeness is not threatening. It is awe-inspiring. The complexity is not chaos. It is order of a deeper kind. You are a traveler tonight, but a traveler in the imagination, guided by the light of science. Every experiment I describe was real. Every equation I mention is tested. The frontier may be hazy, but the path to it is clear, paved with evidence and mathematics. This is humanity's eternal quest, to understand the medium in which we live, to master the flow that carries us from birth to death, to look at the ticking clock and ask not just what time is it, but what is time? So settle in. Let your body sink deeper into the mattress. Adjust your pillow until your neck is perfectly supported. Feel the cool fabric of the pillowcase against your cheek. Let the tension drain from your legs, from your calves and thighs, feeling them grow heavy and still. Let it drain from your back, from the muscles along your spine that have held you upright all day. Let it drain from your neck, your shoulders, your jaw. Notice how your breathing has already begun to slow, how each exhale lasts a little longer, how the pauses between breaths stretch out like seconds stretching in a gravity well. We are going to walk through the gallery of time together, admiring the shapes and shadows, the curves and corners of spacetime, with no rush to get to the exit. There is no schedule to keep. There is no destination to reach before you fall asleep. Let the words wash over you like a gentle tide, rolling in and out, in and out. Let the ideas float by like clouds, some vivid and detailed, others soft and blurred. You don't need to remember everything. You don't need to understand every concept fully. There is no test at the end of this. There is only wonder. There is only the quiet satisfaction of having traveled far without leaving your bed, of having touched the edges of the universe without moving an inch. Breathe, relax. The journey begins now. To understand time travel, we must understand the territory. We often say time and space, as if they are two separate things. A box is in space. A clock measures time. But Einstein taught us to say spacetime. One word, one fabric, one entity. Imagine a loaf of bread. This isn't just any loaf. It is the entire universe, from the Big Bang to the end of time. You can slice it vertically, or you can slice it at an angle. The loaf is the universe, all of space and all of time in a single block. Your life is a long worm wiggling through this loaf. The slice you call now is just one cross-section. Depending on how you move, you are slicing the loaf at a different angle. This is the block universe view. Past, present, and future all exist simultaneously in the loaf. The dinosaurs are still roaming in their part of the block. Your great-grandchildren are already building their cities in theirs. Julius Caesar is crossing the Rubicon. The supernova that will explode in 1,000,000 years is already exploding. In philosophy, this is called eternalism. It contrasts with presentism, the idea that only the now exists. Relativity strongly supports eternalism. If two observers moving at different speeds disagree on what is happening now in a distant galaxy, then there is no single objective now. If your now includes an event that is in my future, then my future must already exist. In this view, the passage of time is a trick of consciousness. We are like a spotlight moving across a dark stage, illuminating one moment at a time. But the stage and the actors are there, whether the light is on them or not. This perspective is profoundly peaceful. It suggests that nothing is ever truly lost. The past is not gone. It is just a different coordinate. The future is not unwritten. It is just unvisited. What feels fixed is often only familiar. It means that every moment of joy you have ever experienced is still there, suspended in the amber of space-time, as real and permanent as a mountain range. Every particle in the universe traces a path through this block. We call this a world line. Your body is a bundle of world lines, twisting and turning together through time. When you sit still, your world line goes straight up the time axis. When you move, it tilts. The speed of light forms a cone around every point in spacetime, the light cone. The future light cone contains all the events you can influence. The past light cone contains all the events that could have influenced you. Outside these cones is elsewhere, regions of spacetime that are causally disconnected from you in this moment. You cannot reach them, and they cannot reach you without moving faster than light. Now, add gravity to this loaf. Gravity is not a force pulling things together. It is a warping of the loaf. Mass tells spacetime how to curve, and spacetime tells mass how to move. Imagine drawing a grid of straight lines on a rubber sheet. Now place a heavy ball in the center. The lines curve. They stretch. If you were an ant walking along one of those lines, you would think you were being pulled toward the ball, but you are just following the curve of the space you are walking on. This is a classic analogy, but let's deepen it. In reality, it's not just space that curves. Time curves too. Near the ball, the lines of time are stretched out. A second takes longer to traverse. Far away, they are tight and short. Objects naturally follow the straightest possible path through this curved environment. These paths are called geodesics. A planet orbiting a star is following a geodesic, a straight line in curved spacetime that looks like a circle to us. An apple falling from a tree is following a geodesic. It isn't being pulled by a force. It is sliding down the time curvature created by the Earth. This is why astronauts in orbit feel weightless. They are not escaping gravity. They are surrendering to it completely, following the natural curve of spacetime without resistance. We, standing on the ground, feel weight because the floor is stopping us from following our natural geodesic. We are accelerating upwards relative to the spacetime curvature. The mathematics describing this curvature are the Einstein field equations. They are elegant but complex. They relate the distribution of matter and energy, the stress-energy tensor, to the geometry of spacetime, the Ricci curvature tensor. In poetic terms, matter grips space and time, bending them. Space and time grip matter, guiding it. The curvature is real. It causes tidal forces, the stretching of objects as they fall. It causes gravitational lensing, the bending of light around massive galaxies. It is not a metaphor. It is the structure of the universe. We can't feel the curvature directly because it is smooth and we are small. But we see its effects everywhere. This geometry is the playground of time travel. If you can bend the sheet enough, can you bend a timeline into a circle? Can you make the path lead back to where it started? This is what physicists call a closed timelike curve, CTC. It is the mathematical name for a time machine. It is a loop in the fabric. If you walk along a closed timelike curve, you move forward and forward, step by step, feeling time pass normally, until suddenly you find yourself shaking hands with your younger self. You haven't turned around. You haven't walked backwards. The universe itself curved the path back to the past. Your world line, the path you trace through the block universe, has formed a circle. It implies that the block universe is not just a solid brick, but can be Swiss cheese, full of tunnels and loops. Thinking of time as geometry takes the panic out of it. It's not magic. It's like architecture. We are asking if the building of the universe has any spiral staircases. We haven't found any yet in the main hallway where we live, but the blueprints don't strictly forbid them. There might be a spiral staircase near a black hole, or one we could build if we had enough energy. The structure allows for wonder. It allows for the possibility that the house of the universe has rooms we have not yet discovered, corridors that twist back on themselves in ways we can barely imagine. Time is local, personal, and quietly real. Let's pause for a micro-recap. We are looking at the universe as a four-dimensional block called spacetime. Gravity is the curvature of this block. Time travel into the future is just moving along a curved path where time flows slower. Time travel into the past would require a path that loops back on itself. A loop that general relativity permits in theory, though we have yet to see one in nature. But theory is one thing. Evidence is another. Let us go to the evidence. Let us look at the experiments that proved the elasticity of the world. Science is a story of skepticism. We don't believe things because they are beautiful. We believe them because they are measured. The elasticity of time has been measured again and again with exquisite precision. Let us travel back to October 1971. The place is an airfield. Two physicists, Joseph Haffel and Richard Keating, are boarding a commercial jet plane. They are carrying 4 cesium beam atomic clocks. These clocks are heavy, delicate, and expensive, worth tens of thousands of dollars each. They have bought a ticket for each clock, giving them names like Clock 1 and Clock 2 on the passenger manifest. They are about to take these clocks on a trip around the world. It was not a glamorous flight. They had to constantly monitor the clocks, ensuring they had power, protecting them from magnetic fields, checking the temperature. They were guardians of time, flying through the sky. They were nervous. The predicted effect was small nanoseconds. If the clocks drifted or malfunctioned, the experiment would fail. They fly eastward, circling the globe. Then they fly westward. They are testing Einstein's twin predictions, the effect of speed and the effect of gravity. When they fly eastward, they are moving with the rotation of the Earth, adding their speed to the planet's spin. They are moving faster through space relative to the center of the Earth, so they should move slower through time. When they fly westward, they are moving against the rotation, effectively moving slower than the clocks on the ground. They are also flying at altitude about 10 kilometers up where gravity is weaker. The calculations are complex, balancing the kinematic time dilation, speed, against the gravitational time dilation, altitude. It was a race between two relativistic effects, speed versus gravity, east versus west. The eastward trip should show time slowing down. The westward trip should show time speeding up. When they landed and compared their traveling clocks to the reference clocks at the U.S. Naval Observatory, the results were undeniable. The clocks that flew eastward had lost about 59 nanoseconds. The clocks that flew westward had gained about 273 nanoseconds. The numbers matched Einstein's predictions within the margin of error. They had successfully traveled through time just by tiny fractions of a second. They had proven that a passenger on a plane ages at a different rate than their family waiting at the gate. The Half-Keating experiment brought relativity down from the chalkboard and put it on a passenger jet. It showed that time travel is a feature of our atmosphere. It is happening to business travelers, to pilots, to anyone who leaves the ground. It was a triumph of experimental physics, done with commercial airliners and sheer determination. But we don't need planes. Nature sends us time travelers every day. High in the upper atmosphere, cosmic rays from deep space, protons accelerated by supernovas and black holes, smash into air molecules. These collisions create showers of subatomic particles called muons. Muons are like heavy cousins of electrons. They are unstable. They decay very quickly. In a laboratory at rest, a muon lives for only about 2.2 microseconds before it falls apart into an electron and neutrinos. Even traveling at nearly the speed of light, a muon should only be able to travel about 600 meters before decaying. Since they are created tens of kilometers up in the atmosphere, they should never reach the ground. They should all decay high above our heads. Yet, if you build a detector on the surface of the Earth, you will detect thousands of muons passing through your body every minute. How is this possible? How do they survive the long journey down? The answer is time dilation. Because the muons are traveling at 99.9% of the speed of light, their internal clock slows down dramatically relative to us. The gamma factor in the Lorentz transformation is large. To the muon, the trip takes less than 2 microseconds. To us, observing from the ground, the muon's life is stretched out, allowing it to traverse the tens of kilometers. From the muon's perspective, space is squashed length contraction, so the distance to the ground is short. From our perspective, time is stretched. Either way, the muon is a time traveler, surviving long enough to reach the ground because it is surfing the currents of relativity. Every time a muon strikes a detector, it is a tiny signature of time's flexibility. It is a visitor from a different time frame, proving that death can be postponed by speed. Let us go back a bit further to 1959. Harvard University. The Jefferson Laboratory Tower. Physicists Robert Pound and Glenn Rebka designed an experiment to test gravitational redshift, the idea that time runs slower in strong gravity. This was an incredibly difficult experiment. The effect of Earth's gravity over a height of just 74 feet is minuscule, a change of 1 part in a quadrillion. They needed a clock that ticked that precisely. They used the Moosbauer effect, a phenomenon where atomic nuclei emit gamma rays with extremely precise frequencies. They placed a source of iron-57 gamma rays at the bottom of the tower and a detector at the top. They fired gamma rays upward. As the light climbed out of Earth's gravity well, it lost energy. In wave terms, losing energy means the frequency drops, the ticking of the light wave slows down. If gravity affects time, the light arriving at the top should be slightly redder, lower frequency, than when it started. To measure this shift, they had to move the detector at the top to compensate for the Doppler effect. They vibrated the detector speaker cone style. It was an incredibly delicate measurement, requiring isolation from temperature changes and vibrations. But they found it. The frequency shift was exactly what Einstein predicted. They confirmed that the bottom of the tower is indeed slower than the top. They confirmed that gravity pulls on time. They confirmed that the basement of a building exists in a slightly different temporal rhythm than the attic. It was the first high-precision test of general relativity in a terrestrial laboratory. And finally, in 2010, researchers at NIST, the National Institute of Standards and Technology, performed a version of this experiment that is almost poetic in its intimacy. They used advanced aluminum-ion logic clocks. These are not just standard atomic clocks. They trap a single aluminum ion and a single magnesium ion in an electromagnetic field. They cool them with lasers to near absolute zero. They are so precise they wouldn't lose a second in billions of years. They didn't need a tower. They raised one clock just 33 centimeters, about a foot, higher than the other. Just a single step. And they measured the time dilation. The clock that was 33 centimeters higher ran faster. This means that if you stand on a step stool, your head ages faster than if you stand on the floor. The difference is too small to matter for your biology, but it matters for the truth of reality. Time is not a uniform blanket. It is a textured quilt, varying inch by inch, shaped by the mass of the earth beneath us. The universe is calm, even when it is strange. These experiments are the anchors that hold our drifting minds to the truth. They tell us that the strangeness is real, measurable, and closer than we think. We have also sent satellites like Gravity Probe B to measure the curvature of space around Earth directly, confirming frame dragging. We have bounced radar signals off Venus and Mercury when they were on the far side of the Sun, measuring the Shapiro delay, the extra time light takes to travel through the curved spacetime near the Sun. And in 2015, the LIGO detectors heard the chirp of two black holes colliding a billion light-years away, ripples in spacetime itself, gravitational waves, washing over the Earth. Each of these is a testament to the fact that spacetime is a physical substance that can bend, wobble, and stretch. We have seen the subtle warping of time in our backyard. Now, let us drift out to where the warping is extreme. Let us float toward a black hole. A black hole is a place where gravity is so strong that the curvature of spacetime becomes infinite. It is a puncture in the fabric, a remnant of a collapsed star, so dense that not even light can escape its grip. When a massive star runs out of fuel, it collapses under its own weight. If the star is heavy enough, nothing can stop the collapse. It shrinks to a point of zero volume and infinite density, the singularity. Around this singularity is a sphere of darkness called the event horizon. This is the point of no return. As you approach a black hole, the time dilation effects become dramatic. Imagine you are in a spaceship orbiting a black hole, and you send a probe down toward the event horizon, the cliff edge of the universe. As you watch the probe fall, something strange happens. It starts to slow down. The light coming from it gets redder and dimmer due to gravitational redshift. From your perspective, the probe never actually crosses the horizon. It just gets slower and slower, fading into the darkness, frozen in time just above the edge. It becomes a ghost, lingering forever at the precipice. This is because time at the horizon stops relative to the outside universe. But from the probe's perspective, everything is normal. It falls straight through the horizon without slowing down at all. It crosses the boundary in a finite amount of proper time and travels toward the singularity. This disconnect between the two perspectives is the ultimate example of relative time. At the edge of a black hole, time stands still for the outside observer. A second for the probe becomes eternity for the universe outside. This creates profound paradoxes about information. If the probe never seems to cross but actually does, where is the information it carries? This is the black hole information paradox, one of the biggest open questions in physics. If you were brave enough to fly your ship close to the horizon and then return, you would experience extreme time travel. You might spend a few hours skimming the edge of the abyss, feeling the heavy gravity, watching the stars whirl overhead. The view would be spectacular. The gravity would bend light around the hole, creating a ring of fire called the photon sphere. You would see the back of your own head as light orbited the hole. But when you pulled away and returned to Earth, you might find that thousands of years had passed. Civilizations would have risen and fallen. The landscape would be unrecognizable. You would be a relic of the ancient past, stepping into the far future. This is forward time travel on a massive scale. It is allowed. It is scientifically sound. It is just a matter of energy and engineering. We call it time dilation, but it is effectively a one-way ticket to tomorrow. It is a form of hibernation where the universe speeds up while you stay still. And what about the other direction? What about the past? This is where the black hole gets even more interesting. Most black holes are rotating because the stars they formed from were rotating. These are called Kerr black holes. The mathematics of general relativity suggests that the swirling of spacetime around a Kerr black hole might create paths that loop back on themselves. The space is dragged around so violently, a phenomenon called frame dragging, that forward in space might become backward in time. The very fabric of reality is twisted into a vortex. There is a region called the ergosphere where space moves faster than light. Inside the inner horizon of a Kerr black hole, the singularity might be a ring, not a point. You could theoretically pass through the ring without being crushed. Some solutions suggest this could lead to a different universe or a different time. In the 1940s, the logician Kurt Gödel, a friend of Einstein at Princeton, discovered a solution to Einstein's equations that described a rotating universe. In Gödel's universe, the entire cosmos is spinning. This rotation drags light and time with it. If you traveled far enough in a spaceship in a Gödel universe, moving against the rotation, you could return to your starting point before you left. You could visit your own past. Einstein was troubled by this. He wondered if it meant his theory was incomplete. It implied that time travel was not forbidden by the laws of physics, but merely depended on the distribution of matter and motion. But the math stood. In a rotating universe, the past is accessible. Another theoretical construct is the Tipler cylinder, proposed by physicist Frank Tipler. Imagine a cylinder of infinite length, infinitely dense, spinning at half the speed of light. Spacetime would be wrapped around it like sugar in cotton candy. If you flew a spaceship around this cylinder in a spiral path, you could travel backward in time. The catch is that the cylinder needs to be infinite, which is impossible to build. However, some physicists suggest that a finite cylinder might work if you use negative energy. Cosmic strings, hypothetical defects in spacetime left over from the early universe, might also act as time machines if two of them pass each other at high speed, creating a Gott spacetime named after J. Richard Gott. The universe we see today doesn't appear to be rotating as a whole, so Gödel's specific solution might not apply to us. And we haven't found any infinite cylinders or cosmic strings. But the fact that the equations allow these solutions at all is tantalizing. It suggests that the barrier to the past is not absolute. It is circumstantial. It depends on the arrangement of matter and energy. It depends on how the loaf is sliced and twisted. But if we can go back, what happens to history? What happens to cause and effect? This brings us to the most perplexing part of our journey. Here we enter the realm of paradox. The most famous is the grandfather paradox. Imagine you build a time machine, travel back to the time when your grandfather was a young man, and you prevent him from meeting your grandmother. Perhaps you distract him or create a traffic jam or something worse. As a result, your parent is never born. As a result, you are never born. As a result, you never build the time machine to go back. So your grandfather does meet your grandmother, and you are born, and you do go back. The logic enters a loop that seems to shatter reality. It oscillates between you exist and you don't exist. It is a contradiction. The universe, which seems to run on cause and effect, should not allow contradictions. It is a logical short circuit. There are other paradoxes too. The bootstrap paradox involves information or objects with no origin. Imagine you go back in time and give Shakespeare a copy of Hamlet. He copies it and publishes it. It becomes famous. Centuries later, you buy a copy and take it back to him. Who wrote Hamlet? The information exists in a loop without a creator. Or the predestination paradox, where your attempt to change the past actually causes the event you were trying to prevent. You go back to stop the Titanic from sinking, but your distraction causes the lookout to miss the iceberg. You are trapped in fate. This problem has kept physicists and philosophers awake for decades. But there are solutions, gentle, sleep-friendly solutions that keep the universe consistent. One is the Novikov self-consistency principle. Proposed by Russian physicist Igor Novikov in the 1980s, it suggests that the probability of an event that creates a paradox is zero. The universe will simply not allow you to change the past in a way that creates a contradiction. Physics will intervene. If you try to stop your grandfather, the gun will jam. The train will be late. You will slip on a banana peel. A quantum fluctuation will divert a bullet. Your actions in the past will end up being the very things that caused the future you came from. You become part of the history, not a disruptor of it. Researchers have tested this mathematically with billiard ball models. Imagine a billiard ball entering a time machine, a wormhole, and coming out in the past to hit its younger self, preventing it from entering the time machine. This creates a paradox. But they found that there are always self-consistent solutions. The ball might come out of the wormhole and hit its younger self just a glancing blow, knocking it slightly off course so that it still enters the wormhole, but at a slightly different angle, which causes it to exit and deliver that glancing blow. The loop closes perfectly. Nature finds a way to make sense. In this view, time is a closed loop. It is a fixed tapestry. You can visit the past, but you cannot change it because you were already there. The past is what it is because you went back. There is no original timeline that you altered. There is just one consistent timeline that includes your journey. This is a comforting thought. It implies a kind of destiny, or at least a robust stability to reality. You cannot break the world. You are part of the weave. What feels fixed is often only familiar. The past is safe from our meddling. The universe self-corrects. It is a system that maintains its own integrity. Another protection comes from Stephen Hawking. In 1992, he proposed the chronology protection conjecture. Hawking noticed that whenever theorists tried to build a model of a time machine, like a wormhole, quantum effects seemed to intervene. Spacetime is not empty. It is filled with vacuum fluctuations, pairs of virtual particles popping in and out of existence. As soon as a path to the past opens up, a closed timelike curve, these particles would be able to return to their own past. They would circulate through the loop. They would loop again and again, infinite times in a fraction of a second, building up infinite energy. This energy surge, a feedback loop like a screeching microphone, would destroy the time machine before it could ever be used. The wormhole would collapse. The space-time would rip. Hawking suggested that the laws of physics conspire to prevent time travel on a macroscopic scale. He famously said this keeps the world safe for historians. It suggests that while the geometry allows time travel, the quantum energy required to sustain it triggers a natural shut-off switch. The Cauchy horizon, the boundary where predictability breaks down, becomes unstable. The universe protects its chronology. It defends its timeline with a burst of feedback. There is a third possibility, the many-worlds interpretation of quantum mechanics. In this view, every time there is a choice or a quantum event, the universe splits. If you go back in time and kill your grandfather, you simply create a new parallel timeline. In that new timeline, you are never born. But in the original timeline you came from, your grandfather lived and you were born. There is no contradiction because the timelines are separate. You haven't changed your past. You've traveled to a different past. This solves the paradoxes but implies a vast, branching multiverse where everything that can happen does happen. So we have three main ideas. Either you can go back but you cannot change anything, Novikov, or you simply cannot go back at all because the door slams shut the moment you try to open it, Hawking, or you go back to a different timeline entirely, many worlds. All suggest a universe that values order. a universe that resists chaos, a universe that is calm, even when it is strange. It is a universe that knows how to keep its secrets. Let's recap. We have seen that forward time travel is a fact of physics, proven by GPS and particle experiments. Backward time travel is theoretically possible in the geometry of general relativity, rotating black holes, wormholes, but faces steep challenges from causality, paradoxes, and quantum stability. Hawking's protection. We are likely trapped in the now, drifting forward, but the view of the past is always there, preserved in light and geometry. We drift now to the edge of imagination, to the engineering of the impossible. In 1988, physicists Kip Thorne and Mike Morris asked a question. Is it possible to keep a wormhole open? A wormhole, or Einstein-Rosen bridge, is a shortcut through spacetime. Imagine the universe is an apple, and you are an ant crawling on the skin. To get from one side to the other takes a long time. But if a worm chews a tunnel through the middle, the journey is short. A wormhole connects two distant points in space and time. It has two mouths and a throat connecting them. If you jumped into one mouth, you would emerge from the other, potentially light years away, in an instant. If you move one mouth of the wormhole at high speed and bring it back, using the twin paradox effect, the two mouths will be synchronized to different times. One mouth will be younger than the other. Stepping through one mouth would bring you out of the other in the past. It becomes a time machine. But the problem is that wormholes are naturally unstable. Gravity wants to pinch the throat shut. To keep one open, Thorne and Morris calculated that you would need exotic matter, stuff with negative energy density. Negative energy is not just antimatter. It is something stranger. Normal matter has positive mass and positive energy. Gravity pulls it together. Negative energy would have negative mass. Gravity would push it apart. It would act as a repulsive force, holding the throat of the wormhole open against the crushing weight of spacetime. Do we have any of this stuff? Surprisingly, yes, in tiny amounts. We have seen hints of negative energy in the Casimir effect in quantum physics. If you place two uncharged metal plates extremely close together in a vacuum, they are pushed together. This is because the vacuum is full of virtual particles. Between the plates, some waves don't fit, so there are fewer particles there than outside. The pressure outside is higher. The energy density between the plates is lower than the vacuum 0 point. It is effectively negative. But gathering enough negative energy to prop open a stargate is far beyond our current abilities. You would need an amount of negative energy equivalent to the mass of a planet or a star. We don't know if such quantities can exist in nature. It remains a blueprint in the library of physics, waiting for a civilization that can harness the power of stars. Then there is the Alcubierre drive, proposed by physicist Miguel Alcubierre in 1994. This is a warp drive, inspired by Star Trek but grounded in general relativity. It works by contracting space in front of a ship and expanding it behind. The ship sits in a warp bubble of flat space. It rides a wave of spacetime, surfing faster than light without technically moving faster than light locally. Because faster-than-light travel is mathematically equivalent to time travel in relativity, this drive could theoretically allow for closed timelike curves. Again, it requires negative energy. Initial calculations suggested it would need more energy than exists in the observable universe. Later refinements brought that down to the mass of Jupiter, or maybe the Voyager spacecraft. It is still a dream of the far, far future. But it is a dream written in the language of valid mathematics. There are other theoretical time machines. The Van Stockham spacetime involves an infinite rotating cylinder of dust. The Deutsch-Politzer space involves gluing spacetime in a specific way to create loops. These are mathematical curiosities, but they show the richness of Einstein's theory. The frontier is hazy. We don't know how gravity and quantum mechanics fit together. General relativity works for big things, stars, galaxies. Quantum mechanics works for small things, atoms, particles. at the center of a black hole, or at the moment of the Big Bang, both are important. But the theories conflict. We are waiting for a theory of everything: quantum gravity. String theory or loop quantum gravity might be the answer. This theory might reveal that the fabric of spacetime is made of tiny, discrete threads or loops at the Planck scale, the smallest possible length. It might show us that time is not fundamental at all, but an emergent property, like heat emerging from moving atoms. Time might be a thermodynamic effect, a result of entropy increasing. If so, time travel might be impossible at a fundamental level, or it might be possible in ways we can't yet conceive. Until we find that theory, the door to the past is slightly ajar. Not wide open, but not locked. It is a mystery we can sleep on. Maybe advanced civilizations have already solved it. Maybe they are watching us now, careful not to disturb our timeline. Or maybe the silence of the universe means that time travel is simply too hard, or that chroniclers from the future obey strict rules of non-interference. Before we return to where we began, before we close this journey through the curves and valleys of spacetime, let us pause for a moment of connection. You are not alone in this exploration. Somewhere, perhaps in another time zone, someone else is listening to these same words, drifting towards sleep with the same images of black holes and wormholes floating through their mind. Perhaps they are in Melbourne, where the morning sun is just beginning to warm the windows, or in Sao Paulo, where the evening traffic hums in the distance, or in Moscow, where snow falls silently in the winter darkness. You are part of a quiet community of curious minds, people who find comfort not in simplification but in understanding, who are soothed not by the familiar but by the profound. If this journey through spacetime has brought you peace, if the strange geometry of the universe has helped quiet your restless thoughts, consider sharing this experience. Leave a comment below about which concept resonated most deeply with you. Was it the realization that GPS satellites are time travelers, aging faster than us on the ground? Was it the image of the block universe, where every moment exists forever like amber? Was it the protection mechanisms, the universe's own immune system against paradox? Or perhaps it was simply the reminder that the cosmos, for all its strangeness, follows rules we can understand, that the mystery is not chaos but structure waiting to be discovered. Your reflections might guide someone else to this place of calm contemplation. And if you found comfort in this exploration of time, there are other mysteries waiting. Perhaps you would like to drift to sleep while contemplating the nature of consciousness, or the origin of the universe in the Big Bang, or the possibility of life among the billions of stars. Subscribe to continue these nocturnal journeys through the cosmos. But there is no pressure, no urgency. You are exactly where you need to be, in this moment, in this bed, in this gentle drift toward dreams. The community is here when you want it, but the cosmos asks nothing of you. It simply is vast and patient and quietly extraordinary. And so we return. Can you still hear it? The clock. Tick, tick, tick. The same rhythm that opened our journey together. The same mechanical heartbeat or digital pulse that marks the passage of seconds in the darkness of your room. But now, after traveling through the laboratories of Einstein and Hawking, after watching muons rain from the sky and satellites drift through time, after contemplating the event horizons of black holes and the theoretical tunnels called wormholes, after standing at the edge of paradox and peering into the mist of the unknown, now that ticking sounds different. It sounds less like a universal drumbeat and more like a personal rhythm, a private path through the four-dimensional landscape of spacetime. Each tick is not a step that everyone takes together. It is a coordinate unique to you, shaped by your motion through space, by your position in the gravity well of this planet, by the trajectory of your world line through the block universe. Your clock and mine are not synchronized to an absolute cosmic metronome. They are synchronized to their own local geometry, to the curvature of the spacetime immediately around them. The seconds that separate your heartbeats are yours alone. The moments you experience as now are a thin slice through the loaf of existence, an angle determined by your velocity and your gravity and your place in the unfolding of entropy. This does not make time less real. It makes it more intimate. It makes each moment more precious because it is uniquely, personally, undeniably yours. We set out tonight asking a question. Is time travel actually possible? The answer, as we have discovered, is layered like the strata of ancient rock, like the nested shells of an onion, like the overlapping movements of a symphony. Yes, time travel is possible into the future. We do it constantly. Every time you move, you alter the rate of your clock relative to others. Every airplane passenger is a time traveler, aging microseconds less than those on the ground. Every GPS satellite circling overhead is racing ahead in time, its atomic clocks ticking faster in the weaker gravity of orbit, compensated by engineers who understand Einstein's equations well enough to keep your navigation accurate to within meters. If you could board a spaceship and fly close to the speed of light, or orbit near the event horizon of a black hole, you could leap centuries into the future while experiencing only days or hours yourself. This is not speculation. It is geometry. And the past? The door to yesterday is more complicated, more elusive, guarded by paradoxes and quantum instabilities and the deep structure of causality itself. The mathematics of general relativity permits paths that loop back, closed time-like curves winding through the fabric like secret passages in a vast mansion. Rotating black holes might harbor them. Wormholes, if they could be stabilized with exotic matter, might create them. Gödel's rotating universe allows them. But we have never seen one. We have never built one. And perhaps the universe protects itself, slamming the door shut with Hawking radiation whenever we try to wedge it open, ensuring that the timeline remains consistent through Novikov's principle, or splitting into parallel branches if we manage to step through. The past is either unreachable or unchangeable, or leads to another world entirely. In every scenario, history is safe. The universe is calm, even when it is strange. What we have learned tonight is not just physics. It is perspective. We have learned that the intuition we carry, the feeling that time is a rigid, universal, absolute container, is a simplification born of our limited experience. Our ancestors never moved fast enough or climbed high enough to notice the flexibility of seconds. They built civilizations on the assumption of simultaneity, and it worked because the differences were too small to matter for the rhythms of agriculture and trade. But when we built technologies that operate at the speed of light, when we launched satellites into orbit, when we accelerated particles to near-light velocities in underground tunnels, the cracks in Newton's clockwork became impossible to ignore. Relativity was not a choice. It was a discovery. It was the universe revealing its true structure, showing us that the stage is not separate from the play, that the container is woven into the contents, that space and time are a single, dynamic, curved, and beautiful fabric. And here is the gentlest truth of all, the one that might ease you most deeply into sleep. You do not need to hold all of this in your mind. You do not need to remember the Lorentz transformations or the Schwarzschild radius or the exact number of microseconds a GPS satellite gains per day. You do not need to visualize four-dimensional geodesics or calculate the energy required for an Alcubierre drive. The universe does not ask you to understand it completely. It asks only that you remain curious, that you stay open to the possibility that reality is richer and stranger and more beautiful than it appears in the dim light of your bedroom. The equations will still be there in the morning, written in textbooks, encoded in satellites, confirmed in laboratories. The knowledge is safe. The mystery is patient. As you lie here now, your body sinking deeper into the mattress with each breath, your muscles releasing their grip on the day, your thoughts beginning to blur at the edges like watercolors bleeding into one another, you can let go of the need to grasp every detail. You can let the images wash over you, the rubber sheet dimpling under the weight of a star, the muon racing down through the atmosphere in slow motion, the twin returning from a relativistic journey to find her sister aged beyond recognition, the satellite high above adjusting its clock to stay synchronized with the ground below. These images are companions for your drift into dreams. They are not assignments. They are gifts. Perhaps, as you dream tonight, you will find yourself floating near the event horizon of a black hole, Watching the stars will overhead and fast forward as time dilates around you. Perhaps you will dream of walking through a shimmering wormhole, stepping from one end of the galaxy to another in a single stride, emerging not just in a different place but in a different time. Perhaps you will dream of meeting yourself, younger and older, all the versions of you standing together in the block universe, your world lines braided like a rope through the 4 dimensions. Dreams do not follow the laws of physics. They are not bound by causality or chronology. In dreams, you can travel freely through time, forward and backward, looping and spiraling, without exotic matter or negative energy or the approval of Hawking's chronology protection. Dreams are the mind's wormholes, and tonight you have earned them. But even dreams are part of the fabric. Even the firing of neurons in your sleeping brain is governed by the curvature of spacetime, by the flow of time shaped by the mass of the Earth beneath you. As you dream, your body continues its slow journey through the gravity well, aging nanoseconds slower than the satellites overhead, nanoseconds faster at your head than at your feet. You are a time traveler even in sleep, drifting through the 4th dimension at the rate dictated by your motion and position, following your unique geodesic through the landscape of existence. You are safe on this path. You are exactly where spacetime has brought you. There is nowhere else you need to be. So listen to the clock one last time. Tick, tick, tick. It is not the sound of the universe. It is the sound of your small corner of it, your private moment, your personal coordinate in the vast ocean of spacetime. Each tick is a reminder that you are here, now, real and present and alive in this particular fold of the fabric. Each tick is a gentle nudge forward, carrying you through the night, through the slow rotation of the Earth, through the orbit around the Sun, through the drift of the solar system around the galactic center, through the expansion of the universe itself. You are moving. You have always been moving. And the motion is gentle, and the path is yours, and the destination is rest. Tomorrow the sun will rise. Light that left the sun 8 minutes and 20 seconds ago. Light that traveled through the curved spacetime around our star, that carried energy across 150 million kilometers of vacuum, that was delayed by microseconds as it grazed the sun's gravitational field, will stream through your window and warm your skin. You will wake in the future, a future that arrived at the rate of 1 second per second along your world line. You will check your phone, and GPS satellites will tell you where you are by comparing the ticks of their relativistic clocks to the ticks of yours. You will move through your day, subtly time traveling with every step, every climb, every drive. And perhaps, in a quiet moment, you will remember that the universe is not a rigid machine but a flexible dance, that time is not a tyrant but a companion, and that the strangeness of reality is not something to fear but something to marvel at. Is time travel actually possible? Yes. You are doing it right now. Not with a machine of chrome and flashing lights, not with a wormhole torn through the cosmos, but with the simple, quiet, profound act of existing in a universe where spacetime is real, where gravity bends the flow of seconds, where motion stretches and compresses the ticks of clocks. You are a time traveler by birthright, a passenger on a geodesic that began at your birth and will end at your death, tracing a unique line through the 4-dimensional fabric that no one else will ever exactly follow. Your journey is yours. Your time is yours. And tonight, as you close your eyes and let the darkness embrace you, as your breathing slows and your heartbeat steadies and the borders of consciousness begin to dissolve, you can rest in the knowledge that you are exactly where you are meant to be in spacetime. The clock ticks on, but you do not need to count the ticks anymore. You can let them fade into the background, a gentle rhythm that carries you deeper into rest, deeper into the peace of letting go. The universe will continue without your vigilance. The stars will keep burning. The satellites will keep orbiting. The muons will keep raining down. Time will keep flowing or bending or pooling or whatever it is that time does in the strange and beautiful geometry of reality. And you can simply be here, now, in this moment, in this breath. Good night, traveler. Sleep well in the embrace of spacetime. Dream of the wonders waiting in the fabric of existence. And when you wake, May you carry with you the quiet knowledge that you have journeyed to the edge of time itself and returned safely home. The universe is calm, even when it is strange.